Okay, so for the final talk of this session, we have Takao Yuyama at RIMS, who will be speaking about groups whose word problems are accepted by Abelian G-automata. Go ahead.
Okay, thank you for the kind introduction. I'm Takao Yuyama from Kyoto University. Today, I talk about word problem for groups and G-automata. Here is the overview of my talk. This talk is based on my work published in 2023 in Development Language Theory. In the paper, I give a simplified proof of the following theorem proved by Elder, Kambites, and Ostheimer in 2008. It states the following. Let H be a finitely generated group, then if the word problem WP of H is accepted by some z to the n automaton A, then for some integer m less than or equal to n, d to the m is a finite index subgroup of H. However, their proof is somewhat complicated and written in terms of geometric group theory, despite of the combinatorial and algebraic setting of the theorem. And also it relies on Gromov's deep theorem on group of polynomial growth. So in this talk, I give a shallower, that is, elementary and purely combinatorial proof of this theorem based on the paper. Okay. This is the outline of my talk. First, I'd like to start with the word problem for groups. Here is the definition of word problem. Let H be a finitely generated group and sigma be a finite alphabet, and rho be a surjective homomorphism of monoids from the free monoid sigma star onto H. Then the word problem of H is defined by the inverse image of the identity element of the group H and the rho. And we write WP rho of H for the word problem of H with respect to the choice of generator rho. Here, obviously, the word problem depends on the choice of generator's rho. However, it is easily to shown that for class C of languages closed under inverse homomorphism, if the word problem of H with respect to some choice of generator rho, then so is for every choice of generator rho. So we can write just WP of H, dropping the subscript rho. Okay. Then one of the most important problem involving the word problem for groups is as follows. Let C be a class of languages closed under inverse homomorphism. Then determine the class of groups whose word problems belong to C. This is a fundamental problem for word problem for groups. Here are some known results about this fundamental problem. The first one is by Anisimov. For a finitely generated group H, the word problem of H is a regular language if and only if H is a finite group. Today, this is an easy exercise, so please try to prove this later. But second theorem is more complicated and difficult to prove. For finite, this theorem is due to Malashub and Danwuti. For finitely generated group H, the word problem of H is a context-free language if and only if H is a virtually free group. That is, H has a finite index free subgroup. Okay. Then a natural question is, how about other language classes? Okay. Then let me introduce some language classes parameterized by group G, called G-automata. Okay, let G be a group, some fixed group, and roughly speaking, a G automaton is a usual non-deterministic finite automaton with some edge labels, which are elements of G. For each edge E of a G automaton, E has usual label small a, which is a letter in sigma or the empty string epsilon. And E also has a label small g, which is an element of G. Then an input string W is accepted by a G automaton A if there exists some path in A such that its sigma star label here equals to W and its G label equals to the identity element of G. Okay. Before defining G automata formally, we need some convention for graphs and paths. In this talk, a graph is a four-tuple gamma where V is the vertex set and H is the edge set, and S and T are functions assigning to every edge its source and its target respectively. That is, by graph, I mean directed multigraph, okay? Then a path in a graph gamma is a sequence of edges such that the target of every edge is the source of the next edge for each I. This is different from the definition in usual graph theory, but this is convenient for our proof. The sources and the target of a path omega are defined as naturally. The source of omega is the source of the first edge, and the target of omega is the target of last edge, respectively. Lastly, a path omega is closed if omega has same source and targets, or omega is the empty word. Okay. Now we can define the non-deterministic G automaton. By G automaton, I mean always non-deterministic one. Let G be a group and sigma be a finite alphabet. And then G automaton is a 5-tuple A, where gamma is a finite graph, and LG and L sigma are edge labeling functions, and P init and P tar are initial vertex and terminal vertex, respectively. Here, note that if we rule out this labeling function LG, then we obtain usual non-deterministic finite automaton. And edge labeling functions are naturally extended to the set of passes E star. Okay. Then a path omega in gamma is an accepting path in A if it starts from the initial vertex P init and it ends in the terminal vertex P tar, and the G label of omega equals the identity element of G. Finally, the language L of A accepted by G automaton A is defined by the set of sigma labels of accepting passes omega in A. This is a definition of G automaton. Okay. Then the class LG of languages accepted by G automata forms a rational cone. That is, LG is closed under inverse homomorphism and intersection with the regular languages. In particular, whether a word problem WP row of H is accepted by some G automaton does not depend on the choice of the generator rows. Okay. Here are some examples of the class LG. If G is the trivial group, then the language is accepted by some trivial group automata coincide with the class of regular languages. And if F is a free group of rank at least 2, then the class of languages accepted by some F automaton coincide with the class of context-free languages. This is somewhat more complicated, difficult fact than the first one. with this second example, we can rephrase the Malashub theorem as follows. Let H be a finite tree generated group. Then, if the word problem of H is accepted by some F automaton A, here F is a free group of rank at least 2, then some free group is a finite index subgroup of H. This rephrased version is similar to the elder Kambites Ostheimer theorem. As restated to here, let H be a finite tree generated group if the word problem of H is accepted by some z to the n automaton, then for some m less than or equal to m, d to the m is a finite index subgroup of H. So this EKO theorem can be considered as the commutative analog of this Malashub theorem. In the Malashub theorem, H is a virtually free group, and in EKO theorem, H is a virtually free Abelian group. Okay. In the rest of the talk, I give a simplified proof of this EKO theorem. Okay. But however, instead of give a proof of the EKO theorem directly, I give a proof of this theorem, which is equivalent to the EKO theorem. It states as follows. If the word problem WP of a finite tree generated group H is accepted by some G automaton for an Abelian group G, then there exists a surjective homomorphism of groups F from some subgroup G0 of G onto a finite index subgroup H0 of H. Here is the outline of my proof. First, I define the notion of minimal accepting paths and show that there are only finitely many minimal accepting paths. And then for each minimal accepting path mu and each vertex p in A, define a monoid M mu p consisting of closed paths in A. Thirdly, I show that each monoid M mu p induces a surjective homomorphism of groups F mu p from the subgroup G mu p of G onto the subgroup H mu p of H. Finally, at least one of H mu p defining the third step has finite index in H by using the following classical lemma called Neumann's lemma. Let H be a group and H1 after Hn are groups, subgroups of H, and A1, B1 after AN, Bn are elements in H. If H is a finite union of these cosets, AI, Hi, Bi, then at least one of Hi's has finite index in H. So at least one of F mu P satisfies the condition in the theorem. Okay. Now I'll explain the details of these 4 steps one by one. Okay. First, we need some notation for subword and scatter subword. Let sigma be a finite alphabet and U and B are strings in sigma star. Recall that U is a subword of B if there is strings X and Y such that X, U, Y equals B. In other words, U is a factor of B. And U is called a scattered subword of B if U and B satisfies this condition. That is, U is a subsequence of B. In other words, U is less than or equal to V with respect to the word embedding order. It is easy to see that both relations are partial orders on sigma star. Then an accepting path alpha of the G automaton A is minimal if alpha is minimal element with respect to the scatter subword relation among the all accepting passes. Then we can show that there are only finitely many minimal accepting paths thanks to the following Higman's lemma. The scatter subword ordering on E star is a well quasi-order. That is, for every infinite sequence omega 1, omega 2, there exists some pair of indices I and j such that j is greater than I and omega I is a scatter subword of j. As a corollary, there are only finitely many minimal accepting paths, and for every accepting path alpha, there exists a minimal accepting path mu, such that mu is a scatter subword of alpha. Okay. Next, I define the pumpable path NA. Let mu be a minimal accepting path in A, and then a path omega is called pumpable in mu if there is an accepting path alpha like this dominating mu such that omega is a subword, not a scatter subword of alpha j for some j. Okay. Let this straight line be mu and this curve be omega. Then if omega is pumpable in mu, there exists an accepting path alpha like this, dominating mu, such that omega is part of some alpha j inserted to mu. Then it is easily to see that in this definition, each alpha I inserted to mu is a closed path, since both alpha and mu are passes in A, and the sum of G labels of these inserted passes are 0, since G is abelian. Indeed, since both mu and alpha are accepting paths, so the G labels of alpha and mu are both 0. And this difference is also 0. Okay. Okay, then now we can define the set M mu P. For each minimal accepting path mu and each vertex P, we define M mu P as the set of sigma, such that sigma is a closed path pumpable in mu, such that the source of sigma equals P. So if sigma is a closed path starting from P, then sigma is in M mu P implies that there exists an accepting path alpha like this, such that sigma is a part of some alpha j inserted to mu. Okay. Then we can show that each M mu P forms a monoid with respect to the concatenation operation. Here is a proof. Let sigma 1 and sigma 2 be elements of M mu P, and mu is the minimal accepting path here, and then sigma 1 is pumpable in mu, so there exists some accepting path alpha such that sigma 1 is a part of these inserted paths, and similarly there exists some accepting paths like this. And then all of these three paths are accepting. The merged path gamma like this is also an accepting path. And since G is a commutative group, the rearranged path like this is also an accepting path. And thus, the concatenation sigma 1, sigma 2 is a part of accepting path. So the concatenation is in the set M mu P. Thus, M mu P forms a monoid with respect to the concatenation. Okay. Then we construct the group homomorphisms F mu P from the subgroup of G onto the subgroup of H. Let's phi mu P is this composition. This is a surjective monoid homomorphism from M mu P onto rho L sigma M mu P. Here, M mu P is a set of edges in A and set of passes in A, and rho L sigma M mu P is a subset of H. It is a submonoid of H. Then the function phi mu P bar from LG of M mu P onto the same codomain is well-defined function thanks to the following lemma. Let two passes omega and omega prime is in E star be subgroups of some accepting paths, and omega and omega prime has same sources and targets. Then if omega and omega prime has same G labels, then the images in omega and omega prime in H are equal. Here is a proof of the theorem. Let omega and omega prime be passes with same sources and targets. Then, since omega is a subgroup of some accepting paths, there is a path like this, such that this red path is an accepting path. So the sigma label of this path is in the word problem of H. And so the image of this red path in H is the identity element of H. And then omega prime has sigma label same as omega. So this blue path is also an accepting path in A. And that's the image of this blue path in H is also the identity element of H. Thus, the images of red path and blue path in H is equal, and this which is equal to the identity element of H. And since H is a group, so the middle part are equal. This is a desired equality of the lemma. And thus, this function, phi mu P bar, is well defined. Then now we define the subgroup G mu P as the subgroup generated by the domain of this phi mu P bar, and H mu P as the subgroup generated by the codomain of this phi mu P bar. And then we can easily extend to the surjective group homomorphism F mu P from G mu P onto H mu P. Okay. Finally, we'll show that these groups H mu P satisfy the hypothesis of the BH Neumann's lemma. First, we show that the following lemma. If T is a scattered subword of sigma, and sigma is an element of mu P, and tau is a closed path starting from P, then tau is also an element of mu P. In other words, roughly speaking, mu P is downward closed set with respect to the scattered subword relation. Okay, suppose that sigma is an element of mu P. So sigma is an enclosed path starting P, and tau is a scattered subword of sigma, and this is also a closed path starting from P. Then, since mu P is a monoid, as we showed before, so the sigma squared is also an element of mu P, like this. And since G is a commutative group, so this rearranged passes is an element of mu P, and thus this tau here is also an element of MUP. Okay, this completes the proof. And as a corollary of this lemma, we can show the following. If omega is a part of sigma, subword of sigma, and sigma is an element of MUP, then there exists some passes omega 1 and omega 2 such that the concatenation omega 1, omega 2 is an element of MUP, and the lengths of omega 1 and omega 2 are strictly less than the size of P. Here is the proof sketch. Let's sigma be an element of MUP like this, and omega be a part of sigma like this board segment. Then it is easy to see that we can remove the redundant cycles in sigma, and this resulting cycle is a scattered subword of sigma. Okay, so by the previous lemma, this is also an element of MUP. This completes the proof. Okay. Now, finally, we can show that H is a finite union of cosets of H mu P's, like this. Here, mu is a minimal accepting path in A, and P is an element of B, and H1 and H2 be elements in this finite subset of H. Okay. Okay. First, let n be sufficiently large integer so that n is greater than the length of every minimal accepting passes. Since there are only finitely many minimal accepting paths, n is a finite number. And then let h be small h be an arbitrary element of the group H. And since rho is surjective, there is some string such that H equals rho B. And also there is some B bar such that rho B bar equals the inverse of rho B. And then since the word B bar to the n is in the word problem of H, which is equal to the language accepted by A, there is an accepting path alpha like this, such that each sigma label of omega I equals B, and sigma label of omega I bar equals B bar. On the other hand, there is a minimal accepting path mu, which is a scatter subword of alpha, such that we have another decomposition of alpha like this. And then by definition of n, since n is sufficiently large, some omega A is disjoint from mu. That is, omega I is a subword of alpha j for some j. Then by previous corollary, we have for some alpha j prime, alpha j double prime, such that alpha j prime omega I alpha j double prime is an element of mu p, where p is the source of alpha j. And hence, H equals the image of omega I in H by the definition of omega I and V. And by this containment, we have this containment also. Thus, H is an element of right-hand side. Okay, so this completes my proof. Okay, that's all. Thank you for your attention.
Thank you very much. So, are there any questions for Takao?
I guess I can ask one thing. Thanks, Takao. So the Gromov theorem and the other complexities of the original proof are replaced by Higmann's subword theorem and I guess the B.H. Neumann theorem.
Yeah.
So the Higmann theorem is non-trivial.
Yeah, Higmann theorem is non-trivial, but I feel this is easier than the Gromov's one. Yeah,
Yeah.
since this is a combinatorial theorem.
Yeah.
Okay.
Are there any other questions? So if not, let's thank Takao again. Thank you.
Thank you.